Hi everyone, this is Ms. Segovia and I'm going to walk you through our Fun with Water Potential practice questions. By now I'm hoping you guys already went through and read the information. This is all super important and it will be included in your exams. On the inside you've got a little sample problem set, but we're going to go over here to the individual practice problems. You're going to want to have your formula chart handy because we're going to be referencing your water potential problems. If your cell's psi p is 3 bars and its psi of the solution is negative 4.5 bars, what is the resulting psi value? So if we take a look at our formula chart here, we'll see our first formula is psi equals psi p plus psi s. So let's go ahead and write that down. Psi equals psi of the pressure plus psi of our solution. And my pressure value, they told us in the problem, is 3 bars. My solution value is negative 4.5 bars. So here you just call upon your elementary math skills, and you should see that the psi of my system is negative 1.5 bars. Oh, if they could only be that easy. On to problem 2. The cell from question 1 is placed in a beaker of sugar water with a psi of the solution of negative 4.0 bars. In which direction will the net flow of water be? I like pictures, so let's go ahead and draw a diagram here. We know that my solution has a total psi of 1.5, but we need to find the value over here. So in our solution, they give us the psi s is negative 4.0. And we know that the psi should be psi p plus psi s. So if we write that out, psi p plus psi s equals the psi of my solution. You might be wondering, how do I get that p value? Because we know that our solution is negative 4.0. So you look back in the problem and you can't find anything in here, but they did give us a huge clue because they said a beaker of sugar water. Now, a beaker is normally an open container. And so if you go back to your formula chart, you'll see right here that the water potential will be equal to the solute potential of the solution in an open container because the pressure potential of the solution in an open container is 0. So it's actually on your formula chart and something you need to know, that your pressure in an open container will always be 0, which means our psi of the solution is negative 4.0. So I'm just going to put a little negative 4 down here to show my solution. Now, that's not what the question was asking me. The question wanted to know is what direction will the net flow of water be? Is water going to go from the solution into the cell or from the cell into the solution? So what I like doing, the thing that rocked my world, was a number line. And so if you do a number line that's vertical, starting with 0 at the top, because your just pure water will be 0 and you can't get any more pure than pure water. And plot our data points. So my cell sits at about 1.5 and my solution sits at negative 4. And if you've ever poured water out, it'd be very rare to see water travel uphill. Water will always travel down. So in this case, it's going from my cell to my solution. So we'll actually see a net flow of water out of the cell. So we would say the net flow will be from the cell to the solution. And I just abbreviate SOLN. If you want to think in terms of tonicity, we always would put hypotonic up on the top, and the solution then would be said to be hypertonic because the solution is taking water from the cell and making it shrink. So that's problem 2. Problem number 3. The original cell from question 1 is placed in a beaker of sugar water with psi s of negative 1.5 megapascals. We know that 1 megapascal is 10 bars. In which direction will the net flow of water be? So let's go ahead, and our cell is still at negative 1.5. In reality, it would have changed a little bit, but let's just go with it. And we're now putting it into this beaker right here. And so we need to find what the psi of the solution is. So they gave us the size of the solution is negative 1.5 megapascals, 0.15, yeah, but we need our stuff in bars. So we're just going to multiply and take our megapascals times 10 bars, and so we're going to get that our solution is also negative 1.5. And so this means that they are going to be in equilibrium. So our correct answer would be no net flow of H2O because the cell and solution are equal. You can also say that they are isotonic, or you could also say that they have dynamic equilibrium, which means that you'll have some liquid going out and while others go in simultaneously, so you still have a movement, but net they stay equal. All right, the value of psi in root tissue is found to be negative 3.3 bars. If you take the root tissue and place it in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the size of the solution and in what direction will the net flow of water be? All right, so here we go again. The value of psi in root tissue is found to be negative 3.3. And so now we're taking it and we're putting it into here. Now we know the psi, psi of a system is psi p plus psi s. In this case, we are in an open beaker, which means that psi p will be 0. So we can disregard it. So we just need to solve for psi s. And the formula for psi s is negative I CRT. So we're going to take our solution's ionization, which is sucrose, so that's going to be 1, times our concentration of sucrose, which is 0.1, and our constant, 0.0831, times our temperature. Now, our temperature is given to us as Celsius, so you need to remember that you always have to convert temperature into Kelvin. So it's Celsius plus 273. Since we have a psi value, a temperature value of 20 plus 273 gives us 293. And by the way, this one right here, that 0.0831, in case you missed it, that is our pressure constant. It will always be 0.0831. So now we just do our mathematical magic, and you should get negative 2.4 bars. So that was half the question. What will the psi of the solution be? Negative 2.4 bars. And then what's the net flow? So again, if you set up a little vertical numbered line, you'll have 0, negative 1, negative 2, negative 3, negative 4. My cell is plotting right here at about 3.3. And my solution is at 2.4. And so since my solution has a higher value than my cell, we'll see the net flow going from the solution to the cell. So this is actually going to cause my cell to get bigger. And so who's ever on top, that is hypotonic. Whoever is on the bottom is considered hypertonic. So I have a hypotonic solution that is causing my cell to increase in mass because it's taking on water. So the net flow is from the solution, the net flow is from the solution to the cell. Boom. On to the next page. Are you having fun yet? I know I'm not. All right. Sodium chloride dissociates into two particles in water, sodium ions and chlorine ions. If the solution in question 4 contained 0.1 molar sodium chloride instead of 0.1 molar sucrose, what is the size of the solution and in what direction will the net flow of water be? All right, so I'm going to use the space on top because we're a little tight here. So here's my beaker, right? And I've got my cell in there, and it's the cell from the previous question. So it had a psi of negative 3.3. And we need to figure out what is the value of my solution to know where things are going to go. So on this one, again, it's an open beaker, so I don't need to worry about the pressure. That means I just need to solve it for the psi of the solution. The solution of the solution. So negative, or psi equals negative I CRT. And so here we're dealing with sodium and chlorine, and that is going into 2 particles. So this is one of the rare times your I will be something other than 1. So right now my I is going to be 2 because this breaks into 2 particles. My concentration is 0.1. My R value is 0.0831. Again, then you get that from your formula chart. And my temperature is not specified, but since it's the same one as last time, we'll assume that it's 293. And now I just need to work mathematical magic. And so multiply all that together, you're going to get negative 4.9 bars. So that is the psi of my solution. And then it also wants to know what is the net flow of water. So if my solution is negative 4.9, and we do our number line, 0, negative 1, negative 2, negative 3, 4, and 5. Here we have my cell. Here we have the solution. And so water always flows down. My cell is hypotonic. My solution then is hypertonic. So we're going to see going from the cell to the solution. So the net flow is cell to solution. Ta-da! Alrighty, a plant cell with a psi of negative 7.5 bars keeps a constant volume when immersed in an open beaker solution that has a psi s of negative 4 bars. What is the cell's psi p? Alright, so on this one, they give us our psi s of the solution here is negative 7.5. But because it has a membrane surrounding it, that means I also need to have its psi p value to know what that's going to be. My solution, though, is an open beaker, and they tell us that the open beaker is a psi s of negative 4. So out here is negative 4. Now, it's in equilibrium. There's no net difference between the two of flow, and so that means whatever the value is on the inside needs to be the same value as the outside. And so if we have my psi of my solution then needs to be equal to the psi of my cell. So my solution, we know, is negative 4. My cell, we're going to look at psi s plus psi p. And so overall we have my psi p plus my psi s. So psi p minus 7.5. And just work your mathematical magic there, and you should end up finding up that your cell psi pressure is 3.5. So as long as the pressure stays 3.5 in that same solution, these guys should have no change between the two. Question 7. At 20 degrees Celsius, a cell containing 0.6 molar glucose is in equilibrium with its surrounding solution containing 0.5 molar glucose in an open container. What is the cell's psi p? So here I've got 2 cells again in my little beaker, and they are equal to one another. So whatever the external is, the internal should also be. And so if I have my psi of my solution should be equal to the psi of my cell. And we know solution is going to be psi p plus psi s. My cell should also be psi p plus psi s. So let's just work one side first. So on the left I've got my solution value. It's in an open beaker, so I know that I can disregard the pressure constant because it should be 0. That means I'm only having to solve it for the negative I CRT on the left hand side. So if I know that my I value, we're in sucrose, so it's going to be 1. My concentration is surrounding the solution is 0.5 molar. Pressure constant is 0.0831. We're at 20 degrees Celsius, so that's 293 Kelvin. Do your mathematics there. You should have negative 12.2, give or take a bunch of decimals. On the right-hand side, psi p plus psi s, we are solving for psi p, so that value is still unknown. But we can figure out psi S because that should be our negative I CRT. And so we're going to have, psi S minus I CRT. So my I value is 1. My concentration is 0.6. R value is 0.0831. And my temperature is 293. So we work that out, and you're going to end up with negative 14.6. So if I know externally here in my solution is negative 12.2, I need the internal to be the same. So my psi p value, in order to be equal to 12.2, has to be 2.4. So psi p equals 2.4. And then that way, the solution is 12.2, and the cell is 12.2 overall. At 20 degrees Celsius, a cell with a psi p of 3 bars is in equilibrium with the surrounding 0.4 molar solution of sucrose in an open beaker. What is the molar concentration of sucrose in the cell? So in this case, my cell is equal to my solution. There's no net flow. So just like before, we should see psi of the solution is equal to psi of the cell, because we're in an open container. Again, I know that on my solution side, I can disregard the pressure constant, and so I just need to solve it for negative I CRT. So to do that, we're in a sucrose solution, so I'm going to have negative 1 times my concentration, which is 0.4 molars, times my pressure constant, which is 0.0831, times my temperature, which is 293. To work those values, mathematical magic, you should have negative 9.7. And then on the right hand side, we have our psi of the pressure constant is 3 bars, that's given to us in the problem, plus my solution constant, which is negative I CRT. So I'm going to have 3 minus 1. My concentration on that one is what we're actually solving for. Then my pressure constant 0.0831. Temperature is 293. So I'm going to get 3 minus 24.3 C. So we can make that a little bit easier. Let's subtract 3 from both sides of our equation. So we have negative 6.7 equals negative 24.3 times whatever my concentration is. And so divide both sides by 24.3, and you'll get 0.28 is equal to your concentration. And that's how you solve that monster. So if you guys have any questions, please let me know. But that is how you work water potential. Thanks.